What we'd like to do today is cover another type of an algebra, and we are going to name it the De Morgan algebra. Last time we considered what we call the Boolean algebra, and we identified its theoretical basis as being a set that has two binary operations, two unary operations, and 10 laws or axioms or postulates. Today we deal with a different kind of algebra, and that is the De Morgan algebra. You'll see that the Boolean algebra is the basis of the algebra of logic that depends on probability theory, whereas the De Morgan algebra is much more general, and it depends on an algebra of logic that is different, definitely, than a Boolean algebra, and it is the basis of what we call possibility theory, or in fact also fuzzy logic in general. So our goal today is to cover the fuzzy De Morgan algebra and compare it to the fuzzy the Boolean algebra in general. The concept of a fuzzy set was introduced by a scientist at the University of Berkeley, California. His name was Zadeh, and it generalizes our way of looking at the word as being Boolean. Boolean, as you know, contains only two truth factors, the 0 and the 1 elements in the definition of the algebra, and that can be translated into yes, no, true, false, white, black, ugly, clean, pretty. The De Morgan algebra generalizes this concept, and in that case, it considers all the shades of white, not just white or black, but in all the shades in between. And consequently, when we talk about something that's being 0 or 1, the De Morgan algebra, as we'll see, considers all the interval from 0 to 1, like 0.5, 0.75, 0.25. And in that case, it allows us to deal with variables that are not specific at the end of the unit intervals, the 0 and the 1. And that makes it very important in describing the world around us. For instance, you would like to talk about, say, the tire on your car not being totally deflated, 0, or totally inflated, 1. Sometimes we can operate devices or deal with any kind of situations in the in-between. And the concept of the fuzzy De Morgan algebra comes in from Eastern philosophies, where the Chinese yin and yang and hot and cold are basically taken into account, rather than the Western approach of using only 0 or 1, true or false, black or white, the extremes of the unit interval. All by itself, you'll see that a fuzzy De Morgan algebra is useful in describing the world around us. However, a combination of both the Boolean algebra and the De Morgan algebra are even more useful, and that's something that we attempted to do here in our own research. I gave you an example earlier in the semester about combining the concept of a fuzzy algebra and at the same time a random variable Boolean algebra. So what is the usefulness of a fuzzy De Morgan algebra? In that case, we do not just define a set. We define what we call a fuzzy set. This is defined as a class of objects with, and that's a key idea here, not just 2 grades of membership like 0 or 1, true or false. By the way, this concept of true or false, or closed and open, the two only opposite the 0 and the 1, is introduced to us by Aristotle. Aristotle was a great philosopher from Greece, a Greek philosopher, and he introduced us to an algebra or a philosophy of a kind of extremes. Something can be either true, completely true, or completely false. There is nothing in between. Something can be a circuit. Let's take a technological example. A circuit can be totally open or totally closed. A pump can be totally operational, perfectly discharging the flow rate that we want, or not discharging anything at all. But that's not what we deal with in the world. We deal with degrees of membership, and fuzzy logic and possibility theory allow us to do that. In that case, we describe a fuzzy set not as the 0 and the 1. The two elements 0 and the 1 are the extremes over the unit interval, or the unit cube, or the hyper cube, as we'll see later. We describe it not by a probability density function, like in the case of random variables. We describe it by what a function that we care, the membership function, or some people call it the characteristic function. And in that case, it assigns to each member of the fuzzy set a degree of membership over the interval 0 to 1. It could be 0.5, it could be 0.75, depending how strong the membership of that object in the over the unit interval. And in that case, it allows us to describe variables that are not the same that we describe as random variables using a Boolean algebra. For instance, you can think about the class of all numbers which are much greater than unity. You could see here the qualification, much greater than. It's a linguistic variable. It is not really a specific value for a number. It's just all the numbers that are larger than unity or 1. The class of tall people, the linguistic variable being tall, does not mean that you have exactly 6 feet in height, or 7 feet, or 6.5 feet in height. The tall people would be a group of people maybe that are from 5.5 feet in height to 6.5. So according to how much their degree of membership in that class of objects, we call it, we describe it by the membership function. The class of operational pumps, so that's a technological kind of example. A pump in a Boolean algebra can be 0, stopped, totally not operating, or 1, totally operating to perfection. Here, it allows us to describe pumps that are operating, but maybe not discharging at their full capacity. An air conditioner could be an air conditioner that runs at half speed, maybe changing the temperature in the room, but it is not blowing at full blast. The class of adequate flow rate, you can have a flow rate that is not 0, nothing flowing, or totally maybe flooding some area with, say, the flow of a liquid. Adequate would be a range of the flow rates, so it takes values from over the unit interval from 0 to 1. Or we can describe something like related to nuclear reactors, in that case, the class of unacceptable fuel temperatures, or the class of acceptable fuel temperatures. So you could see here that we emphasize the linguistic variables that describe the random variables that we measure or observe in a Boolean algebra context. The notion of a fuzzy set is not statistical in nature. It is not a probabilistic. It is its own kind of description of the world around us. So in that case, the formal definition is that we take some space of points or objects. Let's consider it as curly brackets containing x. X could be 1, 2, 3, any kind of objects. And you define a fuzzy set on that space x by what we call the membership function. And I'll give you an example to describe it to you. Now that membership function, mu sub a on x, describes for each point in the set a degree by which that point belongs to that set over the interval from 0 to 1. And in that case, the membership function describes the grade of membership of x in A. For instance, it describes a person's degree of membership in the class of tall people, or his degree of membership in the class of short people. So let us look at an example here, a graphical example. It will describe it to us. Let us take the class of unacceptable nuclear fuel temperatures. So if the fuel has a very high temperature in a nuclear reactor concept, it could melt, and we can represent the class of unacceptable temperatures by that graph right here. It is not a probability density function. It is a membership function. You say it takes values from 0 to 1. 0 would be the temperature. Let's take this point here, 0.1 maybe, on the membership function scale. This would be the fuel temperatures of 100 degrees Celsius maybe. Yeah, we're taking Celsius here. But if you reach a temperature of 600, that is unacceptable to a degree of 0.9. Or if it reaches a temperature of 500, it's unacceptable to a degree of 0.7, and definitely anything above the 700 here asymptotically would have a value of membership function of 1. Definitely any temperature above 700 is unacceptable. So you could see here that it is not a probability distribution. It is not actually also based on measurements. It's based more on guesses or modeling or some expert opinion of what is an unacceptable fuel temperature. The fascinating thing here is that it doesn't follow the laws of probability theory. The membership function simply is a function from 0 to 1. The area under it is not necessarily equal to 1 like a probability density function. So the characteristic function or membership function describes to us the linguistic variables of what we would mean by unacceptable fuel temperature. Notice that it varies from 0 to 1. And that is what a Boolean algebra allows us to use only. It allows us either to use a 0 or the 1 and nothing in between. When in fact, in real life, you find that devices may be operational and we continue operating them maybe even if they have a membership function, say the class of inflated tires. It could be half inflated. We continue operating a car until, say, we go to a gas station and reflate the car in general. Now, the interesting thing is that if you use ordinary set theory that we covered in the last chapter, the degree of membership is Boolean in nature. In that case, it's 0 or 1, true or false. In fact, it could be also said that it is Aristotelian in nature. It follows the Greek philosophy of Aristotle, and as an algebra of extremes. You are an extreme of 0 or an extreme of 1 and nothing in between. And in that case, this is basically Western philosophy in general, follows in life in general, an algebra of extremes. Like if you have a tiff with some enemy, or either that he totally surrenders or totally simply fight you to the death. In Asian and Eastern philosophies, there is always the in-between taken into account. So you could see here, all the area from 0 to 1 is considered in a fuzzy logic, whereas 0 and 1 would be only the Greek philosophy according to Mr. Aristotle. I'm not saying one is better than the other, because if you take only that extreme 0 to 1, you get the descriptions in electronics or the digits 0 and 1, and it's easier to build a circuit that can take a value or 0 or 1. It's much more difficult to build a circuit that can take all the degrees of membership over the interval 0 to 1, but it allows us to describe things that we cannot describe using the Boolean algebra. So in ordinary set theory, the degree of membership is Boolean in nature. In that case, that membership function is always equal to 1 here at that level for all values of x. This is the symbol in mathematics for all values of x that belong to A. And it is equal to 0 for all values of x that do not belong to A. So in that case, you can think about using a step function. Everything below 500 is acceptable. Anything above 500, you get a 1 here, is unacceptable in general. So you could see here that it is not a Boolean algebra. It is a set though, but it follows different rules than the Boolean algebra in general. So in that case, since we are dealing with a different concept in mathematics, we have to do some mathematics. How about defining the zero element or the null element? In that case, we say that the set is empty. And the set is empty when its membership function obviously is equal to 0 for all values of x that belongs to x. And we can show this in a diagram. The membership function can take values from 0 to 1. And an empty set in that case would have a membership function that is 0 everywhere. All right, say 0 all over the place is an empty set. It doesn't contain any membership. In the same way that you have the concept of the 0 in fuzzy, this is what we are calling fuzzy logic now, is a definition of equality. When do we say that a set A is equal to the set B? So the definition of equality is that the membership function for A, shown here from 0 to 1, should be equal for all the points of the other membership function of B for all values of x that belong to x. So we defined here very quickly, the null function is a membership function of 0 everywhere, and the equality process or the equality function is that the two membership functions are equal to each other. All right, so now that's very interesting. Now we have to define the complement. The complement is the same as the opposite, and it has its equivalent in conventional algebra as the minus sign, the negative. So if you have a membership function that goes like this, mu sub a of x, the complement or the opposite or the adjoint, some people call it adjoint, is 1 minus the function itself. So if you take 1 here, minus 0, it gives you the 1. And you could see that 1 minus mu sub a is the complement or the opposite, if you want to call it, of mu sub a. So if you have here the set of, say, acceptable fuel temperatures, this would be the set of unacceptable fuel temperatures, 1 minus the membership function all over the range of the definition of the x in general. We also need to define the containment. A fuzzy set is contained on another fuzzy set B if the membership function of A is less or equal to the membership function of A. And we describe this by saying that A is contained in B, the same as a Boolean algebra, or A is a subset of B, or we can say that A is less equal to B. And in that case, we show it also graphically. You could see here that the graphical representation gives us lots of insight into the toughness of the pure mathematics. So mu sub A here is contained in the membership function mu sub B. So that is a concept of containment, or that there is a subset. So mu sub A describes a subset A of the set B, and each one of them is a fuzzy set. Oh, now remember in the Boolean algebra, we define two binary operations. Simply stated, it's the union and the intersection of the two sets. So in the same way, we need to define in a fuzzy algebra or the Morgan algebra, what is the union of two sets. And we use the union symbol here between two sets, A union B, and we in a Boolean algebra, we identified this union operation as an OR operation in the algebra of logic. We are not interested just in a Boolean algebra or the Morgan algebra. We are interested in the logic algebra that pertains to either one of them. In that case, graphically, if you say that A union B it means that you take the maximum of the two membership functions. And so that's a maximum of the membership function of A and the membership function of B for all value of X that belong to X. And graphically, this is the way we show it. So if you have a membership function of A and the membership function of B, the union, the OR operation, is the maximum between the two functions. You could see here it goes up, then comes down, and then goes up back again. Let's remember this because it will allow us to calculate numbers for the possibilities of an event A or an event B occurring. But we are not describing it with probability density functions. We are describing it by the membership function in that case. In the same way that we define the OR operation or the union operation, we define the intersection operation, which you guessed it already, it would be the minimum between the two. So if I, instead of taking the union between the two sets or the OR gate, we can define the AND gate, which is, in fact, later on the possibility that the A and B in the algebra of logic are really existing. So in that case, instead of taking the maximum, you take the minimum between the two membership functions to represent the AND gate in the algebra of logic. So again, if I have a membership function of A like this, going up here, and a membership function for B going up and then coming down, the membership function for A and B, both occurring, takes this value where we have the circles. Notice something very important here is that the values take values from 0 to 1. And a fascinating thing is that it allows us to describe things that we cannot describe with a Boolean algebra. So let us take the case, let's take actually a case of a cup. And if you think about a cup that is half full and half empty, all right? Now, logic tells us that the cup is half full, but we can also say that it is half empty. In a Boolean algebra, we cannot say that. We can only say that the cup is empty or full. So what do we do in that case? That is the law of the excluded middle, as it's called. All we do is simply take that situation where the cup is half full and half empty and hide it under the rug. We ignore it. We simply forget about its existence when in fact we know logically that it does exist. We say that the cup maybe is half empty if it is an epsilon amount below half the height of the cup, and if it's it is full when it is epsilon, a tiny amount above the halfway through the cup. But look here, as this is, say the cup is full, this maybe the cup is empty, and in between here, you'll find that the cup is empty to a degree of 0.5, and the cup is empty also full to a degree of 0.5. So it allows us really to eliminate the paradox of the law of the excluded middle. We know it doesn't exist in Boolean algebra. We simply, as I said, we sweep it under the rug. All right, so another definition is that two sets A and B as disjoint if their intersection or their minimum is empty. If it's 0 here, those two sets basically are disjoint. They do not appear on the same range of values on the x-axis in general. So in that case, the intersection of A and B, because that's the intersection, it is associated with the AND gate in logic, it is equal to the null set, which is 0 everywhere. All right, so we are ready now to define what is a fuzzy or a De Morgan algebra. Well, it is the same as a Boolean algebra. It is a set, any set. And that set has on it two binary operations. We'll call them conjunction and disjunction. You can call them union and intersection. And then that third operation is a unary operation. The unary operation could be, of course, a complement or the opposite or the less for, the larger than. any kind of complementation that acts on a single member of the set. Those two operations, the plus and the star, or the conjunction and the disjunction, operate only on two membership functions of the set. Notice something very important here. We did not define on the De Morgan algebra any upper and lower bound. The 0 and the 1 do not exist there whatsoever. So you'll find out that a De Morgan algebra has the same laws, axioms, or postulates as what we have in the Boolean algebra, except for the law that tells me that something and its opposite cannot coexist. And if you go back to the previous chapter, you'll find that X and its opposite cannot coexist. That's equal to the null set. In the case of the De Morgan algebra, something and its opposite can coexist to a certain degree of memberships. This means that if you have a cup, it can be empty to a degree of 0.5 in the height of the water in it, and it can be full also to a degree of 0.5 in the height of the water in it. So it's a better description of some parts of the technology or the word that we have. So we have binary fuzzy binary operations. In that case, in the algebra of logic, we take the union and associated with the OR gate, and we take the intersection and associated with the AND gate, and we take the complementation and associated with the basically the complement or the opposite. In that case, it is the OR gate is the maximum between the two membership functions. The AND gate is the minimum between the two membership functions, and the complementation is 1 minus the membership function. Very importantly, you'll find that in a De Morgan algebra, something, remember this is the AND gate, and its opposite in a Boolean algebra is 0. That is the concept of Aristotle that tells us something cannot be black and white, that no shades of gray exist in a Boolean algebra. Something cannot be true or false. Something cannot be open or closed. Something cannot be ugly and pretty at the same time. And in that case, this is the definition of the identities. The X or its complement is equal to 1. In that case, do not exist in a fuzzy or a De Morgan algebra. The same laws that apply to a Boolean algebra do apply to the case. They all exist in the same, in fact, way. The De Morgan law is still there. The distributive law is there. The absorption law, the associativity law, the commutativity law, the idempotence law, except for the law of what we call the excluded middle. In a Boolean algebra, the law of the excluded middle defines the universal bounds or identities. So when you take A and its complement or its opposite, that is equal to the null set. Something and its opposite cannot coexist. Boolean algebra. Something union its opposite is 1. It's everything or the unit set by itself. Those two laws from a Boolean algebra do not exist in a De Morgan algebra or in a fuzzy algebra. We are going to call it De Morgan algebra or a fuzzy algebra. You'll find that the intersection or the existence of A and its opposite does not necessarily be equal to 0. As I suggested, a cup can be half empty, and it can be also half full to a degree maybe of 0.5. And the union of A and its opposite, or the OR gate, does not necessarily equal to 1 like in a Boolean algebra. All right, so this is interesting here, is that basically we can deal with degrees of membership. Something is not 100% true or false. Something is not always black or white. There are degrees of gray. And in fact, you can think about it as in a Boolean algebra, you have a set that has a boundary. However, in a fuzzy set, the set doesn't have a clear boundary. So think about the lights from the headlights of a car having different degrees of intensity if you project them on a screen. All right, so now this is basically the concept of introduced by Mr. Zadeh, the concept of the membership function. Came in another very interesting scientist that I would like to learn about. In that case, he's an engineer. He's an electrical engineer from the university. Let me see, I think it's another, it's not Berkeley University in California. He is, I don't recall, it will come to my mind later. And he came up with a different description that enlightened us about the concept of fuzzy sets. So I did mention that you can take the unit interval, let's say here, 0 to 1. 0 and 1 would be the description using a Boolean algebra. Now, if you use the fuzzy algebra, there are points that exist in between the 0 and the 1. Mr. Costco, I think he's Santa Barbara or in California. He wrote several books on fuzzy logic. He shows us here a unit square. In that case, you could see the values for two variables go from 0 to 1 on the x-axis, 0 to 1 on the y-axis. And then we describe the position of A in that unit square as being 1/4 on this axis and 3/4 on the other axis. And in the fuzzy logic, all the points here within the unit square can be identified. So you can say that my set has a strength in the x-axis of 1/4 and in the y-axis has a strength of 3/4, and all the points in the unit square can be accessed. In a Boolean algebra, only the corners can be accessed, 0 and 0, 1 and 0, 1 and 1, and 0 and 1. And it's very easy to use the unit cube too, right? So in that case, you deal with 3 variables rather than 2 variables like in the unit square, or 1 variable if you deal with the unit interval in general. So he generalized the concept of fuzzy sets as being all the points on the unit square or the points on the unit cube, or even the hypercube that we cannot really represent because we live really in a 3-dimensional world in general. So in that case, the point 1/4 and 3/4, 1/4 on the x-axis, 3/4 on the y-axis represent basically a point in the unit, that's a unit square, not the unit cube, and you can also generalize it to a unit cube in general. All right, so if you take a set A, 1/4 and 3/4, what is the complement of that set? Well, in that case, instead of the membership function, you take 1 minus 1/4, you'll find that this is a point 3/4. And if you take the point 3/4 here, in the complement, it would be 1 minus 3/4 in the same way that we said 1 minus the membership function, it would be the point 1/4. So if we go to the unit square here, that's the point A, 1/4 and 3/4. If you take the complement of A, it will appear right here, which is 1/4 minus 1/4. 1 minus 1/4 would be 3/4 on the x-axis. And then on the y-axis, it would be in that case 3/4 minus 1 minus 3/4, which is the point 1/4. So in that case, in the unit square, if this is a point A, the complement of A, which we are representing with an A with a dash on top of it, would be the complement of A right here. Another interesting operation that comes out on the unit square is the union of A and the complement. And we said that the union is represented by the maximum between the unit between 1/4 and 3/4 on the x-axis. This is 1/4 and 3/4. and the maximum between 3/4 and 1/4. So it's a point 3/4 and 3/4. So in that case, you find that on the unit square, the point here, A union, its complement would be represented here. And in the same way, we said that the AND gate is the minimum between the two functions. So if you take the intersection of the point A and its complement, so it is the minimum between 1/4 and 3/4, which is, of course, 1/4, and the minimum between 3/4 and 1/4, which is 1/4. So we can represent not just the complement of A in the unit square, but we can also represent the union, which is the maximum between the X and Y variables, and we can represent the minimum between the X and Y variable, and the whole square. Now all the values here can be assigned in a fuzzy set, whereas in the Boolean algebra, we only deal with the extremes here, basically the corner of the square. And it's a fun thing to do it using basically the unit cube. So I'll give it to you as an exercise. And for instance, if you take in the unit cube, you would have a point in the cube would have an X value, a Y value, and a Z value. What would be the complement? The complement would be 1 minus 1/4, 3/4, 1 minus 1/2, 1/2, 1 minus 3/4 is 1/4, and you can represent in the unit cube the value of the complement in that case. Or the OR gate would be the maximum between the values of A and its complement. And when you take the AND gate, you take basically the minimum between the values in that case. Oh, well, suppose now that you don't have just one variable, that's a unit interval. Say if you have two variables, that would be the unit cube. If you take three variables, two variables, that would be the unit square. Three variables would be the unit cube. What about, how about if you have four variables? Now that's a hypercube. So in that case, we use the power of mathematics, because we cannot represent really a hypercube in that case. So in that case, we just simply apply the mathematics. So if you have the hypercube set, 1/4, 1/3, 1/2, and 3/4, we cannot show this in a three-dimensional world. The complement would be 1 minus 1/4, 1 minus 1/3, 1 minus 1/2, and 1 minus 3/4. And then if you take the maxima between the values of the points, that gives you the complement, the OR gate. And if you take the minima, you get the AND gate. And this is in essence really the difference between a Boolean algebra, where we have an algebra of absolutes, 0 or 1, true or false, open or closed, ugly or pretty, two absolute values, nothing in between, and we replace it by an algebra that allows intermediate values, and we get over the inconsistency really of the law of the excluded middle in the Boolean algebra. The Costco interpretation is a very interesting one too, in that it gives us some kind of a visual way of visualizing the OR gate and the AND gate. The important result that we got here is that when we have an OR operation, I want you to remember the OR operation is the maximum between the fuzzy values. And let us show this in the diagram right here. The maximum and the AND operation is going to be the minimum between the two membership functions. And we are going to use this in now applications later on. We would be interested in calculating the probability of two events occurring, so that's an AND gate, or one or the other event occurring, that's an OR gate. You'll see that if we deal with random variables only, the Boolean algebra applies, and in that case, we sum the probabilities according to the Venn diagrams when you have an OR gate, and we multiply the probabilities in the case of an AND gate. If we are using a fuzzy variable and we want to say something is full and half full, we take the minimum, and if we want to have an OR gate, something is A or B, we are going to be taking the maximum. And in that case, these are not probabilities anymore. They are possibilities. And there is a very important distinction that we are trying to learn between probability theory and possibility theory. Now, let me give you another idea about a relationship between the possibility theory and probability theory by an example. I don't have that in the notes, so you may take notes about it. If I can open this. Okay, that has been described by Mr. Zadeh. And Zadeh gives us an interesting distinction between probability theory and possibility theory by an example that he wrote in one of his papers. So let us understand the difference between the probabilities and possibilities. So possibility has another intonation. It could be also feasibility or plausibility would have been a better name than fuzzy variable in that case. So let us think about the variable x, any variable x, and let's say that x is the number of apples that some gentleman, let's give him a name that, let's name him just Joe, eats per day. And let's play together that simple game. Now, suppose that I go and ask Joe to keep a statistic of how many apples he eats per day. All right, let's look at the value of the apples that he can eat in one day. Maybe some days he eats 0 apples, right? That's a valid value. Maybe he eats sometimes 1 apple, 2 apples, 3 apples, 4 apples, 5 apples. He thinks that an apple a day keeps the doctor away, and he eats apples every day. If he keeps a frequency and counts how many apples he eats per day, and then he reports it to us, then we can tell how many times he eats 1 apple in a given day, and then we can say, well, okay, he eats 1 apple per day, maybe 80% of the time. So we ascribe to it a probability of 0.8. And how many times, how often does he eat 2 apples per day? We can go up here and say, oh, this is only 10% of the time, and this is here 10% of the time. Now what? These numbers that we generated in that case by actual measurements and actual data, this is what we call a random variable, right? You could see that now the sum of 0.1, 0.8, and 0.1 add up to 1. So because they add up to 1, this is what we call the normalization condition. So this is basically a probability distribution right here. And I'm just connecting it with points, but in fact, it is a discrete function. All right. So this probability distribution is generated based on observations, frequency distributions, and measurements. But what if Joe doesn't live here around us? He lives far away, say in Japan, and we are going to export the apples to Japan. So we ask ourselves a question: how often is it that we can guess that Joe doesn't eat any apples on a given day? And we cannot say it's 0.1. We have to say that, oh, it's very possible. So we put this a cross right here, and that should be at the value of 1. This means that's very possible that he eats no apples on a given day. And if we ask ourselves the question, how often does he eat 1 apple per day? Well, it is very possible. So we put another point here at 1. How possible is it that he eats 2 apples per day? Oh, now we come down maybe to 0.9. And if he eats 3 apples per day, it's very improbable. And we are basically guessing. And then we can connect this points here by dots. Now, this is a probability distribution or a probability density function. This is a membership function. So you could see here that probability distribution is based on observations. A membership function is based on guesses or a model. We have created a model in our mind of how Joe is reacting. And in some cases, when we are designing engineering systems, we don't have data to make measurements on the new design. So what do? We do some guessing. And notice that the maximum value is 1. It cannot be negative. Same for the probabilities. But some very important observation can be made right here. In that you can have a low probability of something occurring, but on the other hand, it can be 100% possible. Do you see that? I'll repeat that. You can have a very low probability of occurrence. You don't see it happen, but oh, it's very possible. For instance, let's take a meteorite hitting Champaign-Urbana. We haven't seen any meteorite hitting Champaign-Urbana, so the probability here, the measurement is 0, right? But is it possible that a meteorite can hit Champaign-Urbana? Oh, definitely. So the possibility is 1. This is a difference between probability and possibility. And we deal in our world sometimes with possibilities or a combination of them. However, as your possibility decreases, then you find that the probability also decreases. So if the possibility of getting a hurricane into Champaign-Urbana is low, then the probability decreases. We are not going to see or observe a hurricane in Champaign-Urbana. So the interesting aspect here is that a decreased possibility implies a decreased probability or observation, but not vice versa. Something that is not observable can be 100% possible. For instance, we don't see around us radio waves, so the probability with our eyes at least is 0, but we know that radio waves are possible in this room. And some people take that to metaphysical kind of level, the fact that maybe we don't see the supreme being because it's hard to observe it, but it is 100% possible. So we have the concept of the existence of the supreme being, God, or any other concept from that perspective. So you could see that this is possibilities. And these are probabilities. And they're not the same. And I'll show you later that, in fact, when you combine both of them, then we deal with information, and it's a better way of describing the world around us in that case. I've come to the end of those 2 lectures, so I'll give you some examples to work on as an assignment. In that case, in the same way that you use the Venn diagrams in the previous chapter to prove the Morgan law, I want you to use the, in that case, what we call the Zade diagrams, those membership function, to also prove the Morgan laws. I remind you, what are the Morgan laws? It's when you take A union B and you take its complement, this is equal to the complement of A, the opposite of A. You change your union into an intersection and you take the opposite of B. This is the first Morgan law, the Morgan law. If you take the intersection of B, that should be equal to also the complement of A, the complement of B, and the intersection becomes the union. This is easy to prove using Venn diagrams, but I want you to use it, the Zade diagrams, those membership function, to prove those 2 laws. Just show the left-hand side and then show the right-hand side and prove that they are the same. For instance, let's take this one here. A, membership function of A, maybe it looks like this, mu sub A, and mu sub B would look maybe mu sub B right here. So what is the complement of A, the union with B. The union A and B, as we said, is what? The maximum. So this is here. All right. And if you take the complement, the complement would look something maybe like this. And then prove the other one, take the complement of A in a diagram and take the complement of B in the other diagram, take their intersection, you'll get the same graph. In the case of the Venn diagrams, it's more straightforward. And we wish you a nice weekend. We stop at this. Next time, we are going to look at applications and translate those very simple Boolean algebra and the Morgan algebra laws into probabilities and possibilities. And I'll also give you something to work on the Cosco hypercube and the Cosco cube in understanding the concept of a fuzzy point in space. Thank you for your attention. We'll stop at that.